Yeah, so I guess like I posted, we thought we could talk a bit about depth. So I have a few slides I can go through. And yeah, Hojae also put some stuff together on structure from motion. And then, yeah, I thought we can kind of start by talking about the thing I always found most confusing was just how parallax works and how it kind of relates to Monty and really just to kind of think through it in concrete terms. And then yeah, eventually this discussion could maybe get into like where is this happening in the brain and things like that. And um, but yeah, unless any objections, I'll just get right into it. Um, so yeah, I'd posted some notes in the group about kind of various things I've been kind of reading about depth perception, and that was kind of like a broad view of everything from monocular to binocular cues and things like that. But I thought the kind of key thing, or like one of the most important things for like actual fine-grained depth perception, and also I felt like one of the more kind of less clear kind of computational things is the role of parallax. So I just put together some slides kind of discussing that, and then some stuff kind of discussing how it kind of relates to active perception of the and the influence of depth. But yeah, definitely stop me if anything's unclear.
Sounds great. I feel like I'm back in college. I'm like, yeah, basic, lecture here. It's great.
Yeah. um, so parallax basically just refers to when you have two different views. Here it's in space, but it could be in time with kind of motion, but kind of two different viewpoints. Um, and they're viewing two different images of approximately the same thing. Any kind of displacement or kind of change in that image is generally what's referred to as parallax. Um, so in this example, if you imagine this is just some kind of telescope, or it could be whatever camera looking out, and then there's this other one. These are the kind of viewpoints. These are the kind of the views that would be perceived at these two locations. And if you imagine these objects are very far away, kind of at infinity, they're going to be kind of coming into these two different locations, basically in parallel. There won't be any difference, and so the same image is perceived. Whereas this much closer object, it's going to be perceived kind of on the right-hand side for this viewpoint and on the left-hand side for this viewpoint. And so that's the kind of shift that's happening, this kind of the star. That's the
Well,
basic idea.
I
So
guess
yeah.
I guess it's worth saying that if you had a bunch of objects at different depths, they would shift different amounts.
Yeah,
So they would sort themselves in order in some sense, distance.
yeah. And the other thing is we tend to, because we have mobile eyes that move, we tend to fixate on, the object of interest. And so to generally think about it, the way kind of we view the world is imagine we have our kind of mobile eyes, we're fixating on an apple. And this apple then, or at least the center of the apple, is going to fall on the fovea of both of these, both of our eyes. And so there won't be a disparity for the apple because of this. So this is different from this kind of situation where you're sort of fixating at infinity. Um, and disparity, which is a term that's often used, is, I mean, I don't think anyone's super consistent with the terminology, but I think the best way to kind of define it is essentially like a computed estimate of the parallax. So parallax is kind of a property of the world, a property of optics. Disparity is kind of what is the retina picking up in terms of the relative difference between kind of where an object is falling in these two images. And as I said, because we can move our eyes, there's no disparity at the fovea for the item we're fixating there. But there is disparity for the orange. And that can then tell us something about its relative depth to the apple. But then what's kind of interesting is that generally that's not sufficient. So this kind of gives you some sense of relative depth, but you can see how in different instances, instance A, where both objects are far away, and instance B, where they're kind of both closer, the relative disparity sensed for the orange is the same based on these angles here. And so in general, this is kind of combined with some additional depth cues, such as like how turned in your eyes are. Here they're turned in much more, so that implies your point of fixation is closer in space. Here they're more parallel, so that
This only
implies
makes a
farther away.
difference if you're trying to figure out the actual distance, right? I mean,
Yeah,
it's still figuring,
yeah,
it still is accurately replaying the relative distance.
right.
It's still saying
Yeah,
which ones are further away than others,
yeah,
which for a lot of tests, that's really all you need is the, you know.
right, right. Yeah, if you're not like reaching to grab something or
Right, right. If you're just trying to, you know, decide where the boundaries of an object are or something like that.
But one kind of important thing for this to work is the eyes, the retina or the eye or the brain, kind of whatever level it's happening, needs to kind of know the commonality between what's being perceived in the two eyes. So in order to kind of sense that the orange has shifted across these images, you actually need to understand that it's the same object that's there. And this is what's known as the correspondence problem. So how do the kind of features that are present in one image correspond to the features in another? And so I think it's important to realize that the brain in general is only solving this at kind of fine levels of detail. And the way it kind of does this, it's believed, is with these kinds of disparity sensitive neurons. So you can imagine at the point at which you're fixating, let's say on the apple, even there's going to be disparity in the images in terms of like what each apple, what parts of each apple are falling where on the retina. And you can imagine having some neurons that have binocular receptive fields. So they're receiving inputs from both eyes. And then they are looking for kind of the same feature, but with some displacement. So to make that more concrete, imagine these kind of simple stimuli. These are going into both eyes. And most of these stimuli are the exact same for both eyes. That's what's shown outside of the red box. And then within the red box, the stimulus has been shifted. So everything outside of the red box, your eyes can easily fuse and perceive as a single stimulus because they're identical. Both eyes perceive the exact same thing. But within this box, this kind of stimulus that's being shown is simulating some disparity that essentially all these black points here have been shifted over by a small amount. And so a disparity neuron would basically have a receptive field. It responds to this stimulus, say, of course, this is just a toy example, but kind of a white box with a black box next to it. But in this kind of retinal space on the retina, it responds at this location, but on this other one, it responds at this location. So it will be sensitive to this precise kind of disparity of that feature. And that basically
these neurons are known to exist? Is this, or is this a hypothesis?
Yeah, so throughout kind of definitely at the stage of V1 and later, they exist. Whether they exist even earlier than
it's
that.
Funny because in this example, the thing that really matters is this: this is as if you're fixating on something at a distance, and there's something that's closer to you that you're not really paying attention to, and so it exists at two different locations on the two different retinas. But that's not really the thing you want to attend to, right? That's the thing in the little rectangle is not the thing you want to attend to. That's just something that's in the way, and you don't want to attend to it.
So here, yeah, so a more realistic portrayal, maybe this is what a more realistic portrayal is there are some things that would be the exact same within the box. That's the point of fixation, but there's going to be stuff nearby around it that's going to shift if there's any depth.
Okay, right. Well,
so that's what I'm trying to emphasize.
Wherever you're fixated, you're right. Wherever you're fixated, there should be commonality, and then where you're not fixated, it should be displaced or have disparity.
Yeah, and so I'll kind of get back to
this example was a little bit odd because the thing in the center was not the thing you're fixating on because it was moving.
Yeah. Yeah, let's maybe assume that this is what you're fixating on, and so that's the same, but everything else
so
is
while we were sitting here, I mean, you can do this real experiment right here while we're sitting here. Just look at a wall away from you and attend to the wall, and then hold your finger in front of your face.
Yeah.
And you'll see two fingers. right?
Yeah.
Unless you focus on the fingers. So that's
Yeah.
the example of what you're just doing there is that, but it's like I'm attending to the wall and therefore the fingers
Well,
get
no.
to.
So I'm trying to show the more fine grained example where this is happening at a small enough level that you have neurons selective to this disparity. So I'll talk about the finger later. The finger is where the disparity is so large that your eyes aren't able to fuse it, and so you see double.
But why would I want to fuse it if it's at a different distance?
Because
Uh,
then if you have a small object like this and you're
it's
focusing on
like
this point,
which
you seen this?
what no.
Uh,
Oh, right there. Okay, you have a small object. You've
a
got
small object like this, you're fixating on here on this corner. There's going to be zero
uh,
disparity there.
I don't see the corner. Which corner?
Let me say I can't actually
Just
see.
just use the words like the red rectangle is the object, right?
Well, that's what I was trying to say. The within the red rectangle is an object, and there's some parts of it that there's the point of fixation. Let's say that's 4E. So that's going to be the exact same across the images,
Yeah.
but everything else is shifting
You're
by a
saying
small
because
amount. And
the
so
object itself has depth. Is that what you're saying?
exactly. So that's why I mean
So
like
like
it's like
I'm
this
looking at a
box.
curved surface of an apple, and
Exactly.
one point the apple is going to be, and the other point is going to be. So, do we know that the brain actually wants to fuse those other parts, or is
It
it
does,
because
yeah.
how do we know that?
I mean, but
I
that's how
mean,
you perceive. That's how you perceive fine-grained depth detail, like the curvature of the surface.
well, so let me just play devil's advocate here. So I'm thinking like a single column looking at this, right? That single column is a patch. I don't, nobody's looking at the entire apple. I'm looking, that column is looking at a patch at a time. So for that particular one column, I guess, the different columns could be looking at different patches of the apple and they'd be at different depths. So for some, I wouldn't want the one right in the center of my fixation may not want this, but maybe the ones that are off to the side or other columns are looking at the side of the apple, which is a little further away. And you're
Yeah,
saying for that column wants to fuse the two together.
yeah.
Okay, it's maybe, I'm not 100% certain of that, but okay, I'll go with it. At the moment, sure.
And then that provides the signal for the kind of relative depth. And what this means is that with these kinds of fine shifts, you perceive depth. So the classic way to test this is with this random dot stereogram, which is something like what is being shown here, but just at a much higher resolution. And basically each eye sees to one eye a totally random stimulus, but because there's correlations across the images that fire up these disparity detecting neurons, you end up perceiving that as a consistent stimulus like
But
a
let
banana or
me
star or an elephant or a
I programmed some of these when I was young. So, but this also works with one eye. I don't need two eyes to see this brute.
yeah, so that's across time. I'm showing it here with time so that we can actually perceive it because I don't have a way to show you two images to your
Right.
separate
Okay.
eyes.
So I'm testing this because okay, yeah, I agree across time. It makes sense. I trust you, but it wasn't obvious to me that this would actually occur without time on a column looking to the side would somehow fuse these two together, somehow route those things. I mean, in general, what we're asking for a column to do, imagine a column is looking at the side of the apple that's just a little further away. And we're asking it to say, oh, I'm looking at a patch of retina, but there's two retinas. And so somehow I have to take the input from those two retinas, which are now those inputs aren't the same, and somehow I have to shift it to make it the same. I mean, I don't know how that would happen.
That's what I'm saying. There seem to be, or at least one way the brain seems to solve it. It's probably kind of multiple solutions, is to have neurons that are essentially hard coded for a particular kind of subtle feature at a particular disparity. So this kind of green neuron here
Oh,
receives
these are
inputs from both the fovea and this point, which is displaced from the fovea, and it's detecting the same feature but with that offset. So that's what I was trying to show here.
right.
That's this kind of
And
receptive field.
these cells are known to exist in the cortex.
Yeah, yeah, you can measure them.
I have a question.
Yeah,
Any idea how, so like in the case where there's static images, you can imagine there's some kind of difference being taken. locally between, we've got input from both eyes. There's some local difference being computed to create these disparity cells. Any idea how you're using motion to artificially drive those?
Yeah, as in like what's happening here.
Yeah.
I think it's just something where, yeah, I haven't thought about it too much, but I think it's just something where kind of the same computation's happening, but there's kind of a buffer, I guess. So that comparison can happen as long as these kind of stimuli are shown close enough together in time. Kind of a similar comparison's done.
Maybe I could speculate on this a bit, right? So the only thing that could possibly fire here, there's no features. The only thing it fires is motion detection, right? So there's a series of points in this image where the motion is being detected. And that is typically would be your magnocellular cells in the retina that detect motion, right? The parvocellular cells do not detect motion. They do not fire when things are moving. But so you have a set of magnocellular cells that are firing at the borders of this thing. And I'm just going to start with that. And then for the columns that are receiving input from those magnocellular cells would say, oh, there's a feature here. There's something going on here. And obviously the feature really is just, it's almost like there's no features here, but there's a set of columns that are active that surround these objects. And it's just that literally it's like saying, oh, there's some feature at this location. There is no feature, but there's something at this location. And that is apparently sufficient to recognize some of these things. I don't know what the image on the right is. I can't even tell what that is. But one of the things I learned when I did this earlier is that your limit to recognize a particular object is very limited in this regard. That is, if you start making something that's a little bit more complicated, you just can't tell what they are at all. And I was surprised when I did that. Here, I can see, oh, it looks like a pepper and a star and well, a star is a different thing, but the elephant, I don't know what that other thing is on the right.
I think it's meant to be like a Jeep, like a car.
Oh, well, I didn't get it. See, I couldn't tell that. So there's a very limited ability to recognize things in this regard. But anyway, I would argue the mechanism is magnocellular cells are firing because they detect change. And so a bunch of columns are being activated at those and that's it. All you have is the idea that there's something here, and maybe you can get the orientation of that thing.
Yeah, I don't think this is necessarily contradictory, but I guess, Scott, like just in terms of like this kind of view of it, where it's not necessarily that dependent on motion. It's more that kind of like at any given point, these cells are going to be getting kind of a stimulus, like I guess one of the stimuli, the first one is going to kind of come here, and then the one that's shown like a quarter of a second later or whatever is kind of firing up that point. And then at the next time point, you get another shift. And so that's why like it kind of gets fused together so that it feels like it's both 3D, but also that it's wiggling. Like it doesn't feel like it's a 3D image that's static in space.
Isn't it true? Isn't it true that there really is no disparity in those images? There's no disparities in these.
But that's the thing. I think the brain perceives disparity because of how closely in time they're presented.
I see. I disagree. I think it's got to be. I mean, then it's a change, right? If the brain this only works because the cells are detecting change. There is never a point where there's any possible thing to look at to say there's a disparity between these two things. It's just edges of change. I'm not saying disparity cells don't exist, but I don't think that they're playing. I'm guessing. I don't think they play a role.
Yeah, in this motion one. Maybe.
I guess the question is like, is this triggering a depth percept for you or not? Like, it's not a very strong depth percept for me. Like, I get this more of a surface texture segmentation, slight depth. Like, it may be driving the depth.
Yeah,
a little bit.
I don't think this is a depth perception example, is it? This is just a figure of ground separation example.
Yeah, I mean, this is a more pronounced example where there's more cues. But I mean, I would argue I perceive this as being kind of almost like a 3D like paper world. Like it looks like they're kind of like paper cutouts that are inserted into a 3D scene. So it's like any individual person looks kind of 2D, but the arrangement of them within this street looks 3D to me.
Right, but I think it's an artifact of just the way this is presented. First of all, you can, all these perceptions, I don't know about the disparity neurons, but almost all these effects can occur with one eye. And typically when you're walking down the street, like if you're walking down that street, your head's constantly just jiggling a little bit one way. You don't have to try to do it. Your eyes don't have to move. That's just natural. And so there will be that kind of, the thing you just illustrated in that street scene will occur in your head. And I think the fact that it feels like two sheets of paper is probably because it's a very unnatural way of presenting it to us. The world doesn't jiggle like that without our motion. Like we typically move our bodies, we sense it. But it's really no different than you just moving your head back and forth a little bit. There's technically no difference between those two things.
Yeah.
And so I don't think you should read too much into it, but other that it feels like sheets of paper. But that effect is what's happening, and it doesn't take two eyes to do it.
Right.
I guess it could be disparity over time. But I
Yeah,
always
because
felt it like,
it's the same. I think it's the same idea ultimately. Like, yeah, disparity over time. Like you still, whether it's over time, and like I guess Hojae's presentation might go into this more as well. Like you still need to solve this correspondence problem, and so the way the brain seems to solve it, at least for static inputs, is to have neurons kind of selectively tuned for these features. But
well, it's interesting because
yeah.
if you think about the street scene, you don't have to solve a disparity problem. You fixate at some point, and then everything that's not that depth, you fixate at some depth, and everything that's not at that depth is changing, so you can just ignore it in some sense. It becomes blurry. It doesn't, if you're not trying to solve the disparity problem. This is when I thought was surprised you mentioned the disparity neurons, because the only way I can imagine that is like you're trying to focus on multiple depths at the same time. And that was the example of the apple, which is curving away from you. That it was like, oh, that's like a different problem. That's like I'm actually trying to perceive multiple things at different depths at the same time. Where normally I've been thinking about this problem, it's like, oh no, I just want to ignore all the stuff that's not I'm looking at the woman and the child, and everything that moves relative to them is not part of the woman and the child. It's something else, and I can tell how far away they are. The disparity neurons would, if they exist, they would say, oh, this is this far away, or that's that far away. As opposed to attending, like fusing them. That's the part that's weird to me, is like we're trying to fuse those.
Yeah, because I guess the way I'm thinking about it is like, say I think the receptive field of a V1 neuron is something like your two thumbs held out at arm's length. So it's not nothing. It is a reasonably decent amount of information, and so it's kind of like within that sort of receptive field, you have a perception of depth all at once. It's not like you only it's not like you always perceive everything that you attend to as just being a single plane relative to everything else.
Well, so like so
it's within that kind of local perception.
But let's say I have two let me explain this. I have two eyes, and they are trying to focus on something that's in the receptive field of that neuron. But maybe the thing that they're focusing on, or the things they're trying to attend, is smaller than the receptive field of that neuron, and it's just smaller. And so normally I wouldn't want to pay attention to things that are further away. I would just want to say, like, yeah, the only features I'm really interested in are the ones that are in focus, the ones that come from both eyes at once, that are aligned. And anything that's not aligned would not be a feature that I'm attending to. And so that would be a quick way of saying, yeah, there's a bunch of input comes from the retina over this area, some size of a little circle or something. But actually, the thing that's of interest to me is smaller than that, and only the axons from both eyes that are co-aligned will be recognized, and the axons that are non-co-aligned won't. They'll just be ignored, because I don't really want to attend to them. I don't want to see more, I just don't want to. I just don't want to see the stuff that's beyond it or closer. So it's funny because you're trying to unite them, and I'm trying to separate them. I'm trying to say, yeah, the things that are further, closer away, I don't want to.
So
fuse together.
I'm agreeing with that for like larger differences. I guess I'm just trying to say that within a small narrow field, there are often cases that we want to perceive true depth there. I mean, that is how primates like are able to like break camouflage, for example, that they can see even if something in a 2D input looks the exact same. It's that disparity at that kind of fine grain that makes stuff kind of pop out.
I'm questioning whether that's true. I don't, the hidden animal pops out because it moves. It's if the animal doesn't move, you don't see it. It just
you can though. I mean, yeah, 'cause, like that's one of the, I guess the innovations or whatever of depth perception is that you can something that an animal that doesn't have depth perception will be unable to see against the background. Something like a primate can because of the 3D depth popping out. Because there's this disparity between.
I'd like to see examples of that because everything I've ever noticed and thought about in this regard is just the opposite. You can't see these things until they move. So I guess all I'm going to say is there's different ways to think about these problems, and I've been thinking about them differently than you're thinking about them. I've been thinking about how it is I eliminate information that isn't at the right depth, and you're trying to somehow fuse information at different depths, which is the exact opposite of what I would normally want to do, right?
Yeah. So I mean, maybe if I move on, because then I'll talk about I think more what you're describing, which is like this is just within a particular area of focus, but then your eyes are constantly moving, constantly looking at different things, and then so that means that, as you say, most things that you're not attending to are not in focus.
Okay, I'm going to still lodge my concern about this idea that a single column's retinal patches are trying to unite different depths. I'm not aligned with that yet. Maybe I'm wrong, but then we can go on.
Okay, yeah. So anyway, so in theory, this kind of having these disparity neurons can help you kind of have this fused percept of some depth in a small area, but this depends on having neurons that are tuned to particular offsets across the two retinas and also particular features, whatever those kind of very simple low-level features are. Of course, you can't have this for all possible disparities and for all possible features. So the reality is,
can I ask? I'm sorry to interrupt again, Niels, but
yeah,
this is research meeting. This is what we do, right? I would have, if I read about this, I would have assumed the disparity neurons are doing something completely different, something that I need to do, and I say, oh wow, they can solve that problem. It's very difficult for a single eye to determine absolute depth, right?
Yeah.
Two eyes can, and one of the problems we have with vision is we have to know, where are we observing thing in the reference frame of an object, and so this if I had a column that was and it had some disparity neurons in it, I could say, oh, I could use these disparity neurons to determine the absolute depth of the distance to the thing to me, and that would be very useful. Not because I want to recognize a feature or unite these things, just to know the actual distance. Just to say, hey, this feature I'm observing, which is at certain depths from me. And therefore the disparity neurons wouldn't be to unite or fuse images, but it would just be to determine the distance to them. I wonder if that idea has been discussed.
That's at least how I understood it from this picture, that this is the purpose of it, to detect the absolute depth. But the way that it does that is it has to recognize which features correspond to each other. And then when it knows, okay, this feature on the left eye retina corresponds to this feature on the right eye, and this is the disparity between them. And that tells it the absolute depth.
Okay, well, in this case, all we need is the absolute minimal feature that will satisfy that requirement. It doesn't have to be a feature that is relative to the object itself, right? I mean, it literally could be a progression of dot differences or something. You know what I'm saying?
Yeah.
It's not like a feature that's on the object that I'm trying to just, add part of my object representation. It's just the minimal thing that could be done that would achieve the disparity.
Yeah, it doesn't
Um,
require any models or anything. It would really just be to figure out correspondence between the two
Right, so
images on
that
the
could be all hardwired and or not, but it could be hardwired. And then, but that makes it not useful for being part of a model. That says, oh, it's not like this is a feature of the object. It's just it's just a feature I'm using to determine depth.
Yeah.
And therefore, I thought Niels was saying we're
Yeah,
trying to
no, sorry, I'm not trying to imply that this is going to be a feature that then becomes part of the object. If that was what it sounded like I was saying.
Well, I guess when I was talking about the apple and seeing on the side of the apple and the depth of it's like, again,
No,
right,
it's more just to get kind of the sort of features we're getting right now. So basically a feature at a location.
no, but it's
So-
not even a feature location. It's just, all we want to do is to calculate distance. That's all we're trying to do is calculate distance. There's no
Yeah,
feature.
Yeah, that's what I mean by a location. But
But there's no feature. It's just distance. It's.
Yeah,
the
so I
actual thing
think-
that's-
how I'm putting it into context also of like Monty is that it seems like what we know about these neurons and vision, that there is a way to extract depth from binocular input very early in visual processing. Maybe like the first input into V1, you can extract depth by taking these disparity neurons, seeing how like what the difference is and getting the absolute depth from that. And this depth is not, it's like Monty gets depth input as like its sensory input features, and it's kind of needed to determine the locations where the actual feature on the model is at. So this
I
is
didn't
like
follow-
what we are doing in modeling to
I'm sorry, I
extract
didn't
that.
follow all that.
Oh, sorry. Yeah, I know that was a bit
In
convoluted.
Monty, we've been assuming a camera with a depth ability.
Yeah,
right?
exactly. So yeah, we assume a depth camera, and I guess now we've been going back into the literature to figure out whether it's kind of reasonable that depth information is available and that this can be extracted without too much knowledge of a model or too much pre-processing. And I guess this would be, at least for me, the context for why we're talking about this
Right,
now.
right.
yeah,
Right.
And on the point of it being hardwired, I posted a summary earlier today about actually how babies learn depth perception. And it seems like at birth, they don't have binocular depth perception, but it is learned very quickly in the first months. So essentially, they first have to separate the input from the right and left eye in V1. So you actually see these stripes in V1 if you put in some dye. And after they've learned that separation, then they learn, then they get binocular depth perception within a couple of weeks, like very quickly. But it seems like after that, it's pretty much, it's quite fixed, because if for some reason a child or a monkey or whatever is deprived sensory input during that formative period, they have like lifelong impairments, like if you are cross-eyed during that period, or if a cat has an eye patch during the first few months, that eye is functionally blind for the rest.
I guess, I was, I slightly misspoke there. When I said it could be fixed or not. What I meant by that is it's not something that you would learn throughout life. It's not like a features, we learn new things throughout life, but I was thinking this would be something that once it's set up, it doesn't have to change.
Right.
And yes, I can see that it could be part of this developmental period, certainly. But when I think in some sense learned, but to me, when I say learned, it's like, oh, I see something new, I'm going to learn it. No, it's not like that. It's like this is a part of the development. You just set this up and then it goes. The thing is interesting about, and I've talked about this before, but in primates, V1 has these extra layers, right? And only V1, and I think it's only
Right.
primates. And I've always said, what the hell is going on there? And it always felt like, well, the difference there is that we're trying to perceive at a distance. Their fingers are right on the the object. You have other ways of knowing where your fingers are. But eyes, we're seeing at a distance where some sound, and so I figured, well, that's really tricky. And so I always felt like, well, maybe those extra layers in V4 are calculating, doing that depth and look, there's a bunch of calculations that have to be accomplished because it's not only the distance, but then when your eyes move, how far they're moving on the object depends on the distance. So you have to know the distance, and then you have to use the distance to calculate the displacement on the object. And so I said, well, that's something that only applies to eyes, and therefore maybe that's what's going on in those extra layers, those input layers. So I still think it's a good hypothesis. I don't know where the disparity neurons exist in V1.
Yeah, so I think there's evidence that could be exactly kind of corresponding to the processing in layer 4. There's at least evidence that that's kind of that's sort of where the first binocular inputs really come together.
Right. And then the way I've ignored that for all these years, because we have this common cortical algorithm, is like, well, we could assume we have a camera with depth, or you can say, look, an animal with one eye is pretty damn good at vision. You can do 95% of what you can do with two eyes with one eye. And so let's not focus on that too much. That was my excuse for
that. And so the core principles of this, of like basically parallax and all this stuff, apply whether it's the two images are across space or they're across time. But
I think there's a big difference between the point of this is to fuse features, or the point of this is to determine depth. And I guess I was reacting to the suggestion that they're trying to fuse features together, and I'm like,
I guess it's just the fusing of the features is a way of perceiving depth.
Okay, as long as
it's a means to an end.
But as long as it's not the features that we're going to apply to an object, like it's not the input to an object as, oh, what is the feature at this location? That is definitely going to be, learned throughout life. You could change what features a column can assign to.
Yeah, I mean, and you could totally do that in this case. Like whatever features are being detected, that could change. So if they're
I'm trying to go the opposite direction. I'm trying to say, like, we're using the features for two different things. There's a retinal feature, which is just whatever the minimum that's required to figure out depth. But then there's features of our object models, and that's something completely different in my mind. And so it's a common use of that word. I'm pushing back on the idea that there's a point of saying, hey, let's fuse these features together and then feed them into our model, as opposed to, oh, we're fusing these features, we're using the disparity neurons just to determine the depth of the neurons that are not disparate, right? The ones that I want to pay attention to are the ones that are actually in plane, and anything that's not in plane is the ones I want to ignore.
No, I think that's, I guess a good way of emphasizing that. As you say, it's what you are fixating on that is the most important. So really, this is just giving you a bit of depth information around that.
Right, that makes sense to me. So it's the kind of language we're using, and it just confused me a bit.
Right, but so this is giving you. So you can almost imagine it's like this is basically saying it would be reasonable for us to assume something like a depth map we currently have, at least near to the point of fixation, just around it. Right. From these disparity neurons, but as said, they can't cover the full space, and so, okay, well, what happens when they don't work, when basically disparity neurons aren't kind of doing what they're meant to do? And this is exactly what we were talking about earlier, Jeff, where if you kind of hold your finger at arm's length, so very easy, if you fixate on it to perceive it as a single object, but then you fixate in the distance, you will perceive your fingers as as being double. It's not confused. And
well, I don't know where you're going with this, but I think in this goal, that's the purpose of the whole system, is not to see the two fingers.
I'm not arguing that it's meant to. No. So my point is just, this shows that it only works in a very kind of narrow. You can almost imagine, if you're familiar with cameras, like a very narrow depth of field is where this is, around where you're focusing, is where that part of depth estimation is going to work.
Right. Okay.
But then in addition to that, then you have all this active perception of depth. And so in particular, you need to figure out where to actually fixate, where your eyes should converge and how much the lenses should accommodate so that you have the kind of stimulus of interest in your kind of fixation. And so initially, if you're, again, just fixating at infinity, then any kind of objects near you are going to be doubled and all this kind of stuff. So somehow you need to estimate where should my eyes actually converge to focus on this tree trunk. How far away is it so that I can focus on it? And then on that tree trunk, let's say there's a beetle. This is literally the example they give as a paper, you know, a beetle with camouflage. Then you could use those disparity neurons to perceive that beetle standing out from the bark of the tree. And so, yeah, so there's different ways that you might do this. This was this paper talked about this kind of contour stereopsis. It doesn't really matter too much, but basically you can imagine you can do kind of correspondence problem for very big, obvious things like, you know, the tree trunk, things like that, so that you don't have these kinds of hardwired, what you call it, disparity neurons for things like this. But it's pretty obvious to each of the eyes that it's seeing, you know, something large like this. And so using that kind of information.
Well, I
or,
like
you
this
know,
basic idea, but you know, it's funny. I'm thinking about the beetle on the bark, right?
Yeah.
And if you, I'm literally thinking about situations like this where you see something and you're not really sure if it's something different. My first reaction is to move my head. I move my head to the side to look at that edge from the side to see if the beetle is protruding from the surface of or if it see if it moves separately from the bark. I think I'm just personal observation is that my ability to determine depth using these disparity neurons is very limited. It's like it's pretty hard to determine if it's a well camouflaged beetle. The whole point it's camouflage means that there are no local features which can be maybe the disparity neurons can work with. And so then I'm just making an observation. The way I would really solve the problems, I would move my head around to the side and look at it from the side and see.
I mean, I guess that will improve the parallax, but yeah, maybe for by the bay, I can bring, I don't know if I can find some camouflage things, because I mean, it's a big thing they talk about in the literature that like one of the main reasons for kind of depth of this fine grayness is how it breaks camouflage. And I think the person who discovered this in like the 50s or 60s, he was actually a military kind of what do you call it, technician who would look at tanks, and they knew in the military that in order to spot tanks that are camouflaged, you need to make sure you give 2 images, one to each eye of the technician, because then using depth it'll pop out. But at the time that wasn't really appreciated in perceptual psychology.
The whole point of camouflage painting is that it doesn't give you it makes it very, very hard to find edges where you can do the disparity. It's like there are, you know, that's the whole point of it. It's like the boundaries of the there's lots of little boundaries and they're matching lots of little boundaries in the background. And it makes it very, very hard to that's the whole point of camouflage coloring, is it makes it hard to pick out those edges that are moving relative to each other. Anyway, I'm just thinking out loud. Well, that's interesting.
Yeah.
I mean, I'm glad I'm sure there's people who study this a lot. I'm just thinking in the back of my head, thinking, what do we need to do for Monty? You know, what are these things? Which of these are appropriate? I kind of already in my mind said like, well, you know, we don't need to have 2 eyes. We don't need to do this converging thing. We could, but it isn't necessary. It's not absolutely necessary. There maybe the bigger thing would be do is to have 2 cameras and just use them for parallax. You know, you bounce back and forth between the 2. They're right next to each other. I'm sorry, I keep interrupting.
No, it's fine. Sorry, was that Will or Rami?
That's me. So are these disparity neurons also useful for calculating how to fixate on an object? So we basically want to minimize the disparity on some objects. So can we use those?
I think so. Yeah, I think for like fine perception, it would make sense that you would use it that like you kind of you coarsely fixate on the tree trunk, but then again, say, you know, something in the middle of it is catching your eye. Okay, that's when you fixate on the beetle or whatever, the tree branch. And then
that would be in this case other than depth. right? It would be yeah, so it would be something else other than just calculating depth, but also how to guide your eyes into fixating on an object just to minimize disparity. So we can.
Well, I don't know if it guides your eyes, or it would tell you when you have fixated on it. It doesn't tell you. I mean, clearly, when you're reading like a small text, you want to keep the letters in focus. I'm not sure these disparity neurons would tell you. They might, but I think to think of them as part of an active perception, I think is a little weird for me. It might be, Rami, but to me, it's more like saying, "Hey, when my two eyes are convergent, there will be some point where there's some depth where these things are co-aligned." And yeah, I guess it could be the way you think about it, but it's just, I don't think it's part of it, like it's not guiding your eyes like saccade over here.
Right.
It could be tweaking the eyes slightly, saying like,
Yeah.
oh, you're a little bit out of focus, move it this way, a little bit out of focus, move it this way. That kind of guiding. That's what I was reacting to. It's not like, oh, move over here. It's more like you're trying to look at this thing, and it could give fine level control to the eyes to say, yeah, just tweak it a little bit, tweak it a little bit, keep it in focus.
Yeah,
If that's what you meant, then I'm with you.
yeah, I agree. The move over here is something probably in maybe high level, but
Right, it would be. So if that's going to be model based,
Yeah.
or motion based, unexpected motion or model based. So I was reacting to the word
Right.
guide. It's like, okay, yeah, it's a limited word for guide. It's just like it's like a local feedback loop to keep things in focus.
yeah. Thanks.
Yeah, and I guess on the model-based point, I think one of the nice things about this, and how we build Monty, is obviously because it has these internal models. That's another very natural cue for kind of having a sense of like, oh, where should I fixate? I'm at my desk. Where do I think my computer is going to be relative to me? I know where it is in the world, so that already gives your visual system some sense of where the eyes should be converging. And then just in general, based on what they do focus on, that gives you some sense of, okay, well, what I thought I was going to focus on is in front of that. And so you can have, kind of an iterative process improving the actual accommodation. But all this, I guess, is just to say that there's kind of this two-stage process, it seems, where you kind of have an initial coarse kind of sense of where this object is so that you can fixate on it. And then the kind of disparity neurons are really just doing this small amount kind of around that point of fixation.
So all my noisy comments were really just I didn't understand that's where you're going. If the disparity neurons are just for this fine tuning of it, then I get it.
Right. Okay.
But
Okay,
using
nice.
the word features and all this stuff confused me.
Right. Yeah, sorry.
The fine tuning mechanism.
But yeah, on a high level, I think this fits in really nicely with what we're doing in Monty, and kind of,
Right.
to me, puts a lot of things into place and kind of validates that it's reasonable for us to assume patches can estimate depth at some level. And
Yeah.
Yeah.
I think,
Yeah,
I'm sure someone's done the math on these things, but if you know the granularity of retinal ganglion cells and the physics, you can determine the ranges of which, the accuracy of which these two mechanisms can work.
Right.
Like, well, how much can these disparity neurons actually correct for? There'll be a small amount. They could calculate that probably, and then what accuracy you get just from parallax and so on. These are all things that I think are estimable mathematically. Right. I'm sure they've done that.
Yeah, I didn't come across any specific figures, but in general, it did seem that people were kind of consistent, I think, with our intuition, talking about very, very small differences for this.
Yeah, it can only work for.
Yeah,
I can only imagine. I can only imagine how it would work for small differences.
And again, we can test it ourselves with this finger example. Like it clearly doesn't work for, and that's not a particularly, I don't know, hard or stimulus. So I know Hojae's going to talk more about motion parallax, but I just thought it was useful to kind of at a high level, or kind of like bigger picture, just kind of touch on the concept or the fact that essentially the same concepts, same kind of mathematics of parallax apply to images gathered over time as they do to binocular, or some animal has even more eyes, or a Monty system has more eyes. It's really the same ideas about the perception from different points in space. And you can see how, again, something like smooth pursuit kind of makes sense in terms of you're essentially foveating at a point in space that's associated with zero disparity, and then kind of everything else is sort of relative to that. And then, but zero disparity, but you have also, I guess, some absolute sense of depth of that location. And I was kind of confused when looking through the literature by just the sheer kind of variety of the terminology used. So if this is helpful to anyone, in general, you can think of motion parallax as kind of broadly equivalent to structure from motion. Sometimes people refer to structure from motion as when the eye is static and other things are moving, whereas if the eye is moving, that's motion parallax. There's a kind of computer vision term of stereophotogrammetry. It's essentially, again, the kind of same disparity matching correspondence problem that's happening in stereopsis that I was just describing, but done through a kind of computer vision process. And then, as mentioned, the structure from motion, and or like whether it's motion parallax or it's stereoscopic vision, again, it's all kind of the same type of thing. So that also means that structure from motion and stereophotogrammetry, it's all kind of using similar algorithms. So these things aren't as distinct as I think they might seem on the surface. And just kind of a last note, going back to what I think's nice about how this all ties in with Monty. So when you are solving this correspondence problem to do this kind of processing in computer vision, it's really computationally expensive and really challenging because they try and do it over the entire image. So, take something like this, 2 images of Notre Dame, and you try find every single point in the image that corresponds to a point in the other image. And that gives you a depth map of the entire image. But, we are concerned with a fovea or kind of a narrow point of perception. And so that would make the problem much easier, much less computationally expensive. In general, I couldn't find much kind of active research on this. Maybe there's stuff in robotics that I missed, but I think it kind of makes sense because, of course, there's not any Monty-like systems that are just perceiving the world through these kinds of narrow kind of apertures. Everything tends to kind of be trying to view the whole world all at once.
It's funny, just showing the picture of Notre Dame there, it reminds us, this is why disparity neurons can only work locally, because the computational requirement to do this over the whole image is requiring disparity detection over very long distances. And
right.
That's
Exactly
what we said. That's exactly what we said. Disparity neurons can't do that. Neurons can't do that. They're gonna have to do something very local.
Right.
So that's just a reflection of the fact that it's just a different way of looking at the same thing. It's just saying, yeah, that's why disparity neurons can't have to be simple, but small.
Right. No, thank you. Yeah, exactly.
Yeah, and also
go ahead.
Just integrating over neurons that come from the entire visual field into V1 would be crazy. I mean, yeah, I don't know, I found this image very helpful for myself, at least. I don't know if you can see this second screen share.
Yes.
But, yeah, basically the stripes that form in V1 after the first learning period, where like they correspond to input from the left eye versus the right eye.
These are ocular dominance columns, right?
Yeah, exactly.
Stripes.
Yeah. The ocular dominance columns. And yeah, so if we have like a little cortical column, it can integrate over a small difference in left and right field between these two inputs. But like if we would look at the entire picture and find correspondence, we would have to look from over here to all the way over.
Right. That's another way of putting it. Exactly. It's like you can imagine during like a neuron doing maybe 1 or 2 stripes, but
yeah.
Beyond that, it gets a combinatorial problem.
Yeah. Right. Nice. Yeah. So I just had one last slide, is just that to kind of summarize, in general, extracting depth from either binocular moving images is not easy, even kind of for biology. And as I was just kind of showing you, it's a really hard problem in computer vision, but fortunately people have kind of worked out the algorithms that we need to do given to kind of 2D images to solve that correspondence problem. but it's much more tractable if you have something like Monty, where you're moving in the world, so you can get kind of crude estimates of depth, fixate, and then you just have this fine estimate. And that fine estimate is just over a kind of a narrow view of the world. And so, yeah, basically the kind of tenets of what we're doing, which I thought was a nice kind of a happy accident, or I guess in terms of what sort of depth information we need.
Yeah, very
That was
nice.
great. That was nice summary. I'm glad we discussed it and debated it. I have a better understanding now.
Cool, thanks. Yeah, and it definitely helped me because, yeah, but I read kind of snippets of Parallax, but it never really kind of made actual sense. But it was nice to see that it kind of fit in with what we want to do.
Of course, I've kind of concluded long ago, maybe erroneously, that most parallax occurs because of motion. I mean, maybe Hojae is going to talk about that. Is that what you said?
Yeah, so I didn't really touch on that that much, but I mean, one of the cool.
I thought you said Hojae was going to talk about that.
Yeah. But I guess I was just going to say one of the cool papers that I came across was how basically mice, they kind of detected almost like this depth map already in V1, precisely in the setting where the mice kind of aren't moving around. Of course, it's just in the the field of one of their eyes, but through motion parallax. So I think there's almost better biological evidence that depth from motion parallax emerges really early than depth from binocular fusion.
Well, and of course, rodents don't have binocular vision.
Yeah, I think they have a little bit just in front of them.
It's a little overlap, but I wouldn't call it binocular vision.
Right.
My perception is that they have no binocular vision because the center of their visual fields are just can't align. So there's a touch overlap on the edges. Maybe that works. I don't know. But my assumption's always been like, no, they're more for detecting predators all around them as opposed to discerning things that prey that they might find in front of them.
Right.
I have some thoughts I want to mention about this, but we'll wait till Hojae's time. We have time.
Yeah, mine's pretty short. So the only thing that I'm saying is that all this in computer vision, there is some kind of ways that we can estimate some depth. Let's see. That I think has a lot of parallel to what Niels talked about. So there's many cues that allows us to perceive depth. I mean, so Niels mentioned like convergence and like accommodation. I'm still like learning these terms, but there are many ways that we can perceive depth. The one that we've been kind of focusing on in this presentation was parallax. So parallax can happen. So I think we talked about this a lot, but can happen because we have when you have binocular vision, because we have like some interpupillary distance. That is one way parallax can happen, and then the other way that it can happen is through motion parallax, which can be in monoculars. If you have one eye, we can still estimate depth. I'm not sure how good, but I also agree with Jeff that with some like physics and math, there's probably a way to estimate like how accurate we can be, though that's not the focus of this presentation. Structure from motion is a way to perceive depth using, I guess I like to call it one eyeball and a movement, which is what I think Monty's distant agent is already. That's the setting that we have. So
again, is this movement of the object or movement of the eye?
Movement of the eye, movement of camera or eye. Yeah.
Okay. All right.
Yeah.
So how's that? Yeah. How is that different than motion parallax?
I don't think so.
Okay. All right. Because you had motion parallax and then a separate bullet is structure for motion. So I didn't understand.
Okay. No. Yeah. So I
think it's
this is what I was trying to get at. Yeah, exactly. It's like the biological term versus the computer vision term.
Okay.
Yeah. We can come back to a 6-second video later. So I think I guess the main argument that I'm making is that in Monty, we can just with the current settings that like without any extra cameras or changing the settings, we can remove the information coming from depth and still be able to estimate depth with what we have currently. But I guess the caveat is that I'm not sure if that depth map is going to be as good as like the ground truth one. So yeah. So this is kind of like the classical kind of output from structure from motion.
Is
So
this the cool
people
video?
have, no, it's not the cool video, but
Oh,
yeah.
damn.
But this is, I guess, another cool video. So basically, you know, there was a research where people took a bunch of images from Flickr. So all these kind of black triangular cone things are cameras. So when you apparently, I guess, when you upload pictures to Flickr, you can some like phone information, I guess, location information is stored, and you know you have the corresponding picture, and people try to use those pictures from Flickr to try to reconstruct this Colosseum in 3D. And there's like a bunch of other examples in this website called Building Rome in a Day. So what you saw was the Colosseum here, but there's a Trevi fountain. This one's pretty cool too. Yeah, because a lot of people take, you know, pictures of these kind of like landmarks. But nowadays, like structure from motion is used in like a lot for like mapping like terrains. Like they would send out drones, take pictures, and try to like map out.
So they're actually, in these videos, they're actually creating a 3D model, because you could make the same video just by linking together images. But they're actually,
yeah,
are they creating a real 3D model, or are they just linking
they're
together
creating
images?
point clouds. They're creating point clouds. The output are these
In
points in
three-dimensional
3D
point
space.
clouds.
Yes,
And then
yes,
they figure out what it looks like in different, so they could
yeah,
view the system from a novel direction.
yes,
Okay.
Yeah, and
yeah.
I guess just to hammer home the kind of parallels between the stereopsis and structure from motion. Like in this instance, you could argue that this is kind of stereopsis, but where you, instead of binocular vision, you have 1,000 cameras all viewing the same thing at the same time. I think it's just helpful
Yeah.
to kind of recognize, I think that, yeah, the sort of
Yeah.
calculations that you need to do to work out the depth of what you're seeing is basically the exact same.
Yeah. So I guess already from this kind of point cloud, it reminded me a lot about Monty, because we do make graphs / point clouds of objects. So these are very kind of detailed because there's thousands of cameras, but the minimum requirement, let me go back to this, is just, you know, 2 images. So like, so, you know, theoretically, it's possible to reconstruct 3D structure from as I guess it starts from 2, and then we can refine it as we take more images or as we do more steps in Monty. Okay, so SFM is the technique to which utilizes series minimum of 2 2D images to reconstruct 3D structure. And the final output is point cloud. They're similar to 3D models that output by LiDAR sensors, which are more expensive. And the minimum requirement is that the 2 pictures, there should be, again, correspondence. You know, the features need to be visible across those 2 or 3 pictures. More is better. And the idea is, I guess, the mathematical idea is that if, you know, in this 3D world, the kind of a camera is capturing lights from different parts of the 3D world, and we're taking an image. So in this case, point 1, you know, ends up here in this first image. Point 2 ends up, you know, a little bit to the right in this image. But if we move the camera, now, you know, the point in 3D is projected to this location in 2D, etc. So that's sort of the setup for this. And whoop.
Does the camera actually have to be in motion for this, or can it just use a lot of different points of view?
The camera, so you can have like 2 people with 2 different cameras taking the picture. It doesn't need to be like that one camera need to be like moving. Oftentimes this is like extracted also from like video, where like, you know, one person has the same camera and is moving across time. But like in the Flickr example, those are all probably people's iPhones, I don't know, or Samsungs, taken at different time. Yeah, so very little.
Well, it's interesting because most cameras
Requirement.
have 0 depth ability, right? So,
Yeah.
but if we're doing this with eyes, we just talked about all the different ways that we can determine depth. And so in Monty and in eyes, you don't have to move, right? You can just be in one spot as long as you can see the points.
Yeah. So the overall algorithm is fairly simple, and I think has a lot of correspondence to what we talked about earlier in Niels' presentation. So just go through kind of each one. Try to put a picture of what that algorithm means without using math. But so the first one, extracting feature. So a feature in this case is not feature in location, but the retinal features, I guess, that Jeff mentioned, like features from image that the sensor gets. Okay,
Well,
one day
if
I'm
you're
going to
going to
put
do it, if you're going to do it this way, like do the
yeah.
whole image at once, then you
Yeah.
need more than just the retinal feature.
Yeah. So I'm
the
not.
retinal feature
Yeah.
only works on that very small distance. You can say, oh, there's an edge and it's moved over a little bit. Here, I have to say there's a gazillion edges that it could correspond to. I have to say, no, this particular cornice that is over here is this particular cornice over there. So it has to be much more complicated features in this case.
Yeah. Yeah. I think that this. So in Monty, I mean, obviously the example is a picture because nobody is. Well, not nobody, but not a lot of people upload pictures of like the mug very close by. So for example purposes, this is like the whole building, but I think this would work. I'm not sure how well with like the 64 by 64 small images that we see in patches for Monty. You can imagine those instead of these two pictures. But anyways, it's like the point I'm making is that it's not yet. This step can happen in the sensor modules without having gone to the learning module, so we haven't learned those features yet. Anyway,
Well,
so
it can't be done on the big scale like this, right?
no, it cannot be done in the
Right.
big
It can only be
for
done
Monty,
very,
yeah.
very locally. It can be done very
Yes,
locally.
yeah.
Which doesn't tell
So
it doesn't tell you where that feature is in the overall object. It just tells you,
yes,
right.
yeah. So yeah, I mean, our pictures or the Monty pictures are, we have usually a very small 64 by 64. Usually, it's like a very zoomed in picture of a mug, right? Like the kind of images that Scott has like showed me. But still, I mean, whatever the underlying image is, let's say there is a way to extract some kind of feature, like a feature from computer vision, such as Shift or some, deep learning is like another thing, but we don't need to use that. But anyway, so first step involves identifying some features, and then next step is the correspondence problem. So when we have features from one step and we move a little bit, and then we have a new image, then we need to be able to match those features. So this is the correspondence problem that Niels talked about. I mean, mathematically or like computationally, this comes down, the features comes down to like in computers as a vector for this particular location. Basically, there will be some vectors, and basically we're trying to find similar vector values. We can do like a Euclidean distance between these vector values to see how close they are. I'm just trying to kind of make this like more concrete how this might be done on Monty or
But Hojae, didn't we agree that this is exactly not the thing we want to do in Monty? This is the computer vision way of doing things, but Monty doesn't look at images like this and try to figure out the different parts. I just want to make sure that what I'm understanding is.
Yeah, like I think this is useful to see how it's done in computer vision, and yeah,
Right.
maybe we would take
Right.
approximations of this, like to what you were saying earlier,
Right.
Jeff. Like we
But this
could
is
use much
not what
simpler
we-
features and just in a local area and all this.
Right. This is exactly what we don't want to. This is the kind of things we want to avoid in Monty. Monty does 1,000 brains basically does a patch at a time and integrates them in space as opposed to trying two images at a time. And so the only important thing is understand for that patch, where is it in space, and the next patch, where is it in space, and the next patch, where is it in space?
Yes, I guess in Monty it would be maybe slightly useful in the case where we have a small patch moving, but it's not being moved by the agent itself, or we have an object moving in the patch. But so it could be an alternative to using optical flow or a similar approach to that, kind of track how the sensor is moving.
I didn't understand that. I mean, there's no place in mind you should ever be looking at the entire image and trying to correlate across the
Oh,
entire
yeah,
image.
yeah, no, I'm thinking of
Yeah,
this more as
that
like,
agree.
what does the approach do? So replacing the image of the cathedral with like a small patch on the object. And then the idea is basically just, okay, we have a small patch. Now that small patch moved over a little bit. How do we find out how much it has moved? We do it by finding specific like low-level features.
Right, doing it very locally again, maybe.
Yeah, exactly.
Yeah, yeah,
Right.
Yeah, so I think
yeah,
It's
again,
a complex because how much you move depends on how far away it is, right? And the orientation. Imagine also you're looking at the facade of Notre Dame from the side, from a skewed angle. You know, you have even more difficulty because you're moving in depth as well as moving, laterally. It's really kind of complicated.
yeah. So again, for example, for this, there's this nice cathedral. For practical purposes, think of replace these images as patches that Monty sees, the 64 by 64 patches. The tiny, tiny little spot. So anyway, between the two patches, we'll, if we go this route, we can extract some features. We'll try to match some features between two patches. And then I'm kind of skipping a lot of the math here, but basically, if we have the corresponding features, then there's some epipolar geometry that we can do to put these kind of images in 3D space in the same kind of same coordinate system. Unfortunately, I use common reference frame, which I feel like overloaded the term a little bit, but basically this process, I guess, overall is called, I hadn't go into the math here, but there's a process called triangulation that we are able to, once we have these two images with corresponding points, that we can estimate what the 3D point is. And I know that that's the whole point of knowing this, but yeah. And then just for the algorithmic sake, the final bundle adjustment is when you have, so we do this starting with two images. So this algorithm is iterative in a sense that, okay, once we're done with the two images, we'll try to add a third one, fourth one, yada, yada, yada. And that's what the final kind of point is. And I have a better visualization of this. So yeah,
I think it
so
starts
it's
falling apart. That idea starts falling apart when we're talking about patches. Again, typically what we'll do is we'll fixate someplace and then we'll move some distance and we'll fixate again, and we'll move some distance and fixate again. We don't move our eyes smoothly over an object, sort of doing this integration smoothly. It doesn't happen, and we don't want it to happen that way.
Yeah, maybe if something else is moving, like if there's a moving object, like a car driving past or something.
Yeah, I know. Maybe. I think we should analyze that problem separately. It's like a different task.
Yeah.
Or just it's just an object, even if it's not moving, it's just like behaving like a bird is flapping its wings in front of you or bobbing its head or something like that.
So
that's a separate problem.
Yeah. Yeah, so that's the end of my what structure of motion is. It's one of many ways to estimate depth. With I think probably the least minimal requirements, I guess, like one eyeball is fine, one movement is fine, and then we don't need like two eyeballs,
Right.
like changes in Monty. I think we're kind of agreeing, Jeff. Like I don't know how well this will work in patches. In computer vision-y terms, it's because I think the patches are quite featureless. There's not like a lot of interesting edges, interesting features, like in the cathedral example. And so one, there's not that many features, and two, because when we see one patch,
there's a lot of edges. There's a lot of edges on the cathedral, right? I mean,
yeah.
In some sense, it's almost defined by a bunch of edges.
Yeah.
But it would only work locally, right? We've agreed this. We're not going to try to do this the way they did it in these computer vision systems, where they're trying to, right? Yeah. It's something that can be done locally. I mean, in the bottom line, just jump to the conclusion here. I mean, it's really interesting to know how biology does this. But if we had a perfect depth camera, we wouldn't need any of it, right? Is
Yeah.
that correct?
Yeah, it's just interesting to
that's
know
right, yeah.
whether we can make that assumption that we can have depth at this
Right,
level.
right. And if we
Yeah.
needed something else, we could ask ourselves, oh, maybe we'll use LiDAR, which is a different depth. That's another depth camera. So
Yeah, I
so
guess-
it's really and it's also useful to say, well, why is this extra machinery in the neocortex with V1? Because maybe it has to do these computations, but we don't have to do those computations.
Yeah.
Right. Yeah, I guess one of the reasons we were talking about it was or there was a few things. I guess, yeah, in terms of applications of Monty, like depth cameras are expensive. A lot of people don't have them. So it was just interesting, like what we can do with 2D cameras, since that seems to be sufficient for people. There was, yeah, to Vivian's point, kind of the biological matching. Like at the moment, we're assuming this depth information is available basically in the first cortical column. Does that mean that we are kind of somehow making incorrect assumptions about what cortical columns can do? Like, what if the first cortical column wasn't, what if V1 was entirely responsible for getting the depth information in the first place? Then like we'd have to rethink what the columns are doing or something. Fortunately, that doesn't seem to be the case. And then, yeah, I guess those were the main two, but that was kind of what led us down this train of thought.
It seems if we wanted to, it's an interesting question. If we really had to do some sort of cost reduction or a different type of camera, I suppose you could go to just having two cameras, like two eyes, just separated by some space. Of course, the larger the distance, the better parallax you'll get. And build a system that works like that. Where you can even just alternate back and forth and determine depth from it. But that would be all outside of the cortical column. It would be all in the sensor module. The sensor module would get input from both these cameras and figure out what to do with it. So that would be one thing we could do.
Yeah, I think one other thing I'd come across that I thought was useful to remember, whatever, is just that like depth cameras are generally quite limited in that so they tend to work by projecting some form of light. So for example, they use this time of flight algorithm or this kind of structured light
Right.
where they kind of output that. And basically in both cases, they then measure that light when it comes back to them. But
Right.
that fails very quickly, for example, in daylight. So depth cameras are very difficult to use.
Well, except for
outdoors.
LiDAR, right? LiDAR is popular.
Right.
Right.
Because
But LiDAR, so yeah, I guess also expensive. Anyways, I guess it's just it's nice that what the brain does seems to be kind of robust in a lot of different settings.
Right. I don't know the current state of the art of depth cameras. I thought they were pretty cheap these days because they have them in game consoles and things like that. Maybe they're not very good.
Yeah, I'm not sure the one in. Yeah, I think ones like I think decent ones like the Intel RealSense one or whatever can cost nearly $500.
I mean, there's a depth there's an infrared depth camera in my phone, right? Don't they use infrared depth information to do face recognition on a phone?
Yeah, that's why we did the Monty meets world with the iPhone, because it has this camera in it. But to get a standalone one is not that easy. I think actually buying a gaming console is the cheapest option.
All right. Well, I mean, we don't have to worry about, there's what it costs us to get one and what it costs to build one. Obviously, they're not very expensive. They're putting them in every phone. They're going to be really cheap. Those are going to be, pennies, $1 max, I imagine, on a phone, something like that. So they can be built cheaply. We don't have to worry about that right now, unless we need to go out and buy one, then we can worry about it. but in terms of the limitations of a Monty or limitations of sensorimotor learning, it's not really a concern. There's lots of ways of getting around it.
Yeah, I feel like a nice maybe takeaway from all the reading that we've done is that if we need to revisit this and kind of build depth perception from 2D images, there's lots of ways we can do it that fit really nicely with Monty and stuff like that. But yeah, to your point, that we can probably just keep using the depth camera like we are for the moment and not worry
think
about
it. Think about the ultrasound system that we've talked with the Gates Foundation about. We talked a long time ago. I don't know if you guys talked since. That's an interesting. There's like a camera that is I don't know. I assume they must get depth perception from that, but they also you really can't interpret those images at all until you start moving the sensor. And that is not like a saccade, that's like a continuous motion, or maybe, I don't know, I have to think about that some more. I'm just thinking there's a practical system that you might want to, it's like a camera, and it's moving, but it doesn't move like eyes. Something else to think about.
Yeah, and
Yeah.
actually, so that reminds me of the third point that I forgot about of why we kind of wanted to talk about this was that, you know, we have some of these challenges, like how do we recognize after a lifetime of exposure of 3D, the 3D world, how do we recognize images in a 2D picture or a painting? And
Yeah,
it
that's a
was
good
just kind of
question.
thinking about, you know, what kind of information from depth perception and how that emerges could kind of inform that. And so I think what was interesting from that is as you kind of, I think everyone would have guessed, you know, there's lots of monocular cues for depth perception that don't have anything to do with movement. And so that's things like shadow and lighting and
Or
perspective and
even
all
just
this kind of
relative
stuff.
size. You know,
Yeah,
if I have if I have a
Yes.
set of features, and let's have a set of features of the letters in a word, and now all of a sudden the letters on one side are smaller and the letters on the other side are smaller, and it has the right sort of skew to the whole thing, you would say, oh, this word is facing away, it's moving away from me. It's like it's in depth. It's rotated in depth in plane. So there's size cues too, I guess.
That's an
Yes.
interesting one because this one actually relies on having learned models.
Right.
We only have a couple of minutes here. Can I just throw out something to think about?
Yeah.
Something that's been something I've worried about. Well, not worried, but I've always, it's sort of puzzling, and I haven't really thought about it too much, but it's related to this. Think about an animal learning in a model of its environment and the grid cells in the entorhinal cortex. The reference frame is a plane in the plane of the environment. It's like a map on the surface of the environment, right? But we never see that view. We don't look down upon our environment from above. We don't look down like we're looking at a map. We're seeing it skewed from the side, and the views we see are never the model we end up with is not what we observe. We observe these different skewed things, and yet we end up with this model, which is like a map. And you can see this too. It's very difficult it's very easy to draw a map view. If I asked me to draw a map of your house, but if I said, draw what your living room looks like looking through the door to the kitchen, which is something you see all day long, it's going to be really hard to draw that. And unless you're a practice artist and you've learned to practice on depth perception issues. So there's this sort of gap between what we actually observe and then what we actually, the model we actually present, which is not, there's a gap there. And the same thing I think is true for you. We assume right now there's three-dimensional models in Monty. And if you assume you have like a finger touch-up sensor, it's not a problem. But visually it would be a problem. It's like if I'm looking at an object visually, like a face, and I'm seeing faces at skewed angles to me all the time, the model I have of a face is more 2D. It's like, oh, there's a nose in the middle and 2 eyes and mouth, but that's not usually what I see. Usually I see these very odd looking things. And so it's the same problem exists in cortex, that there is this, I don't know if you understand the problem, why it's so puzzling, but how do we convert from what we see to what we actually map? Maybe
part of this is maybe a little confounding factor in there is like the decoding problem, basically that we're not very good at drawing in 3D, but if you would actually walk into a room and it would look different from that perspective, you would be surprised, like you would make the correct predictions for how the 3D face would look like, or how the room would look like. So the model must be 3D and have it stored.
But
I feel like even mental imagery, like if I imagine my kitchen and things, or if I imagine someone's face from the side, like I feel like I can have a pretty good, certainly way better than I can draw.
Well, that's the
image
thing.
of what it looks like.
It's interesting because, well, first of all, how do you learn that model from your observations? And clearly, when I see a face from an angle, I will recognize if something's wrong about it. Clearly, right away. but it's not a generative model. I can't say, oh, let's draw that. It is extremely hard to draw a face that's even slightly realistic. If you've tried it, try it sometimes. It's really, really hard. And it just can't do it. And so it's like you have this model. It's more like, to me, it's like you have a model of the environment that's reference frame is anchored on the floor. It's like a map of the floor in some sense. And yet somehow we're able to, on the fly, generate 3D images. Not that we can create them, but we would know if they're wrong. And we can infer from those skewed views and skewed angles, no problem whatsoever. In fact, that's how we do it almost all we do. And yet the model itself is not that view. I have this other meeting here now in a couple of minutes. I have to run to it. I'm in the office today, believe it or not. I'm in the mental office. I haven't been here in months.
Yeah, maybe we can
basically
post in the group,
problem.
because I think we've talked about some stuff around the bottleneck of goal states and how, which I think is what Vivian was kind of also getting to earlier, and how that
basically that the model is in the column, but then when we actually want to produce actions to draw it to draw it, we can't just take the model and put it on paper. We have to send action commands to our hand to draw it, and because we can't communicate the entire model, we recognize mistakes when features come in, but we can't
But think of it this way. I mean, there's a huge amount of evidence in the entorhinal cortex that the models are basically two-dimensional, and somehow we're able to tack on three-dimensional objects onto that two-dimensional model and then generate views of it. I mean, I don't know. I'll leave it to me, it's a puzzle. We're not doing this in Monty. We're just doing direct, like, oh, we have an XYZ location and write it down, and our models are three-dimensional, and we could in theory, anyway, this goes back to the question, in the brain, are all these models really two-dimensional and with 3D appendages? Or are they 3D? And I'm not so certain. I mean, this is, because grid cells are basically two-dimensional, and yet somehow they work to do this three-dimensional modeling. Anyway, I just wanted to throw that out as we're talking about these issues about vision. This problem really surfaces in vision, and that's all I want to talk about. It doesn't surface with touch, and so that's another sort of mystery of vision in my mind. How does that work?